So in this video on hemoglobin, I'm actually going to go through several slides here to talk about how we modulate or shift binding for oxygen. And so this is an important big picture theme to think about. And so kind of starting with this very general slide here, and then we'll kind of map on some content that we actually already had from a different video. But when we look at a binding curves always have the concentration of ligand on the x-axis and sort of the amount that you are bound to that ligand on your y-axis. In this case, for the specific case of hemoglobin, we have fractional saturation for oxygen. But generally, this represents fractional binding as a function of the concentration of ligand. So what we're going to talk about in this video are the different ways that we can affect or modulate oxygen binding to globins. And specifically, we can see here's myoglobin. Myoglobin binds oxygen very tightly, has a P50 value here, right, of a very small value. Actually, let me shift to the next slide here where we're actually going to see that, right? Here's the P50 value for myoglobin of 2.8 torr, so it binds very tightly. And as we have a higher P50 value, remember what that P50 value means. That P50 value is the concentration of oxygen you need to be at to be half bound. And again, that's a population sort of situation. So half of your molecules of hemoglobin are bound to oxygen. We have a similar P50 value here for hemoglobin, right? Larger value, 26 torr. And this larger P50 value reminds us that hemoglobin binds oxygen less tightly than myoglobin. And that's an important piece because that allows us then to transfer oxygen from hemoglobin to myoglobin. So big picture thing, if we see a binding curve shift to the right, that tells us that we have bound our ligand less tightly. So we're going to talk about ways today that we shift and affect this binding. Okay, 3 things that we're going to sort of talk about. We're going to talk about pH. We're going to talk about carbon dioxide levels. We're going to talk about 2,3-BPG, and then we'll also talk about the concentration of oxygen that you have. And with both of these plots, let me flip back just to one that doesn't have so much rating so it's not so confusing. We can see that as we increase the concentration of oxygen, both of these curves go up. Right? And there's other videos that highlight where the shapes of those curves are different. It has to do with cooperativity of binding. But by increasing the concentration of oxygen, we can have a higher fractional saturation. Okay, so let's think about this from a pH effect. This is called the Bohr effect, and we can define just generally the Bohr effect as the acid-induced release of oxygen from hemoglobin. So this is the acid-induced release of oxygen from hemoglobin. And if we look at sort of this Perot's equation, again, another video separately sort of explaining this, but if we look at this equation, this will kind of explain from an equilibrium shifting standpoint. We really should show that this is an equilibrium sort of arrow here. That when we increase the concentration of protons, decreasing pH, this equilibrium will shift to the left, okay? We are going to now protonate our hemoglobin molecule. We haven't gotten into the structural details of where or how it's protonated. And again, understanding that it's not that protons and oxygen bind in the same place, but they are mutually exclusive. So if you protonate hemoglobin, it has a shape that now is not conducive to binding oxygen. It is T state. Okay, so let's just very generally look at these 3 curves, and hopefully you can see that we've got a curve that shifts to the right. So that should indicate that we have something that is binding less tightly to oxygen. So if we kind of go through and label here what's going on here, here's sort of our normal state, pH 7.4. But as we go into an acidosis state, we drop our pH, this binding curve shifts to the right. That's what the Bohr effect tells us, that we are going to bind oxygen less tightly. And if we are in an alkalosis state, okay, what we're going to see is we actually bind oxygen more tightly. So remember when we learned about looking at plots and we drew horizontal and vertical lines. If we want to think about what this means for the P50 value, I'm going to draw a horizontal line here across at the fractional saturation of 0.5 or 50%. And what we can recognize is that the normal P50 value of 26 torr becomes a larger P50 value when we are under a state of acidosis, binding less tightly, requiring a higher concentration of oxygen to sort of have the same 50% binding. Or we have a smaller P50 value. We bind more tightly when we are in an alkalotic state. Okay, so that's what we get from drawing our horizontal line. We want to know what happens to the P50 value, right? That 50% saturation value as we intersect. And we can see that we increase our P50 value as we become more acidic. Now, another thing that we can look at is our vertical lines. And what this vertical line is going to do us is it's going to highlight the fact that we have, looking at the same sort of environmental concentration, we can see that fractional saturation becomes less. So as we keep or we stay at the same PO2, so the same environment, the same kind of oxygen concentration, what we can see is we are going to decrease our fractional saturation, okay? So looking at this again another way, if we are at venous conditions under sort of normal hemoglobin, okay, we might unload to maybe about 30%, okay? But if we are under an acidotic condition, we're gonna dump that bucket of oxygen more. So watch that bucket brigade video if you want to see our sort of bucket dumping analogy. But we are going to have a higher fractional saturation if we are under alkalotic conditions, more basic pH. Okay, so big picture that we sort of want to remember here is that a binding curve that shifts to the right indicates that we are binding our ligand more loosely. So let's write that down here. So binding curve that shifts to the right means that we bind our ligand more loosely. We bind our ligand more loosely, or said another way, less tightly. Right? And so this idea of seeing these binding curves shift in this direction, okay, shifting to the right. Now, this is not saying our state. This is shifting to the right. We shift to the right here. We are going to see that we bind that ligand less tightly, more loosely, okay? And what we're going to see here, and I'm going to map it onto the slide that we just had before, we can see, remember we talked about the importance of the position of this point, right? We talked about the position of this point, right? Changing the position of this point is key. So changing the position of this point is key, okay? So if we want to sort of modulate how much our hemoglobin is dumping its bucket of oxygen once it gets down to venous conditions, we need to think about where that point is, okay? And that's the point that we were talking about with this slide when we talked about the effect. And if you need to, go back and watch this video on kind of hemoglobin binding. And we talked about the difference between these 2 points highlights the effect of loading and unloading hemoglobin as it goes between different environments. And the difference in magnitude between these two spots, these points, represents sort of the magnitude of transfer of oxygen between hemoglobin to myoglobin. And the greater that distance is, the more this point is lowered, the greater efficiency of transfer, the more of our bucket of oxygen from hemoglobin is dumped so that myoglobin can pick it up. Okay, so that is the Bohr effect. That's one way that we can actually shift a binding curve to the right, which means we bind oxygen less tightly, so we are releasing it sort of to the environment there. The next thing that we can sort of think about is other small molecules that can facilitate this. So we're going to talk about 2,3-bisphosphoglycerate, but I kind of want to just highlight and review here. There are 3 ways that we can increase oxygen unloading We just talked about one of them. The first one is we can decrease pH, we can increase our H+ concentration, and that is the Bohr effect. Okay? The second way, and that's what we're kind of showing on this slide, is we can have a small molecule that binds to and stabilizes the T state. And this molecule is 2,3-BPG. So we can have a molecule that binds to and stabilizes the T state. Okay? And if you bind to and stabilize the T state, you are going to unload more oxygen. Okay? And the molecule that specifically we're going to refer to with this is 2,3-BPG. And we're not going to get into the structural details of how or why, but it binds to and locks in that T state conformation, which means it's going to facilitate the unloading of oxygen. The third thing that we can do, and it's related to what we'll see on this figure, and we'll look at this figure in just a second, is higher concentrations of CO2 are going to be a way that facilitate this. So looking at carbon dioxide can react with the N-terminus of hemoglobin protomers. So this is going to be the N-terminus of hemoglobin. And I'm going to get kind of small here at the bottom, so we'll try to keep it all on the page here. What's going to happen is you are going to generate what's called a carbamate. Okay? So this is a carbamate. So you basically change the functional group on the end of your hemoglobin from something that was positively charged to something that is now negatively charged. And what this does is this change in that protonation state, if you will. It really resembles a protonation state, changing from positive to negative. It's not a protonation state, but it changes the charge, really affects where that N-terminus wants to be, and it causes a change in the conformation such that you favor the T state. So again, this shifts to T state. So all of these things are ways that we are going to shift our binding curve to the right. So let's take a second and look at, again, this fractional saturation as a function of oxygen concentration. And what we can see is when we have stripped hemoglobin, and stripped hemoglobin means it does not have this small molecule, okay, and it does not have any carbon dioxide as in there. So we're kind of like considering this baseline system. And without those, we actually bind oxygen more tightly. We actually shift this binding curve to the left with stripped hemoglobin. But as we start adding in some of these things that we say bind to and stabilize the T state, we shift that binding curve to the right. Remember, T state is a shape that is not conducive to binding its ligand, so that means it's going to bind it less tightly. We shift that binding curve to the right. So all of these situations with BPG, with CO2, so you can see CO2 alone, BPG alone, BPG plus CO2 basically gets back to what we see in whole blood. So we do know that those two factors are ones that are really helpful for making hemoglobin in, the in vivo system sort of behave like we'd expect. Okay. So the last piece to talk about here, and a little bit of time here to take on this slide, is to highlight what happens under high altitude. So I'm sure you've experienced, if you're hiking someplace and you're at a high elevation, oh man, you just feel like you just cannot catch your breath. And that's different when we talked about carbon monoxide poisoning and we talk about that suffocating from the inside out. What's happening there is your hemoglobin constantly has carbon monoxide that's bound to it. And as it's traveling around your circulatory system, it never has an open spot to bind oxygen, so you never can deliver oxygen. What happens with high altitude adaptation, and we're going to see this on this slide in a second here as I sort of map it out, the concept is that you never fill up your bucket of hemoglobin with oxygen fully. So you still only dump out to the same level. Your bucket never fully empties Okay, we know that for hemoglobin. It's not that it's a 100% sort of delivery system, but the problem is because you don't fill up completely when you go to the kind of the arterial well, if you will, in your lungs, because you can't fill up completely because the oxygen concentrations aren't as high, then you just don't deliver as much. So that's kind of the nuts and bolts of it. So let's talk about sort of what happens here under normal conditions, under what happens early on with high altitude, and then talk about, well, what does your body do to adapt? Because lots of athletes will actually train at high altitude, and we'll talk about sort of what happens there. Okay, so 3 situations to sort of talk about here. The first situation is going to sort of be our normal situation. So our normal situation here represents, we're going to be sort of at sea level. So let's kind of go through and highlight this. This is going to sort of be our normal level. So with our normal level, when we're taking a breath in, our lungs are going to sort of experience sort of those normal, fill your bucket up completely with oxygen. Okay, so this is sort of our normal situation. So we're going to fill up completely to there. Okay. And then what's going to happen as your hemoglobin sort of travels through your bloodstream, okay, you're going to get down to basically this point. And so this 38% that's right there represents kind of the amount that your bucket unloads, okay? So we sort of have a 38% delivery of oxygen. And I've said this multiple times, but just highlighting, this does not mean that one of your hemoglobin molecules unloads 38% of its oxygen. That doesn't happen. What it means is a population of hemoglobins that are bound to oxygen, 38% of that population gives up all 4 of those oxygens. The other, 62% of the population stays bound to all 4 of its oxygens. Because remember, hemoglobin binding oxygen is an all or nothing. All 4 of those protomers are either R state and all bound to oxygen, or all T state and all letting go of their oxygen. So now let's consider what happens kind of early on if you find yourself in kind of a high altitude situation. So our second scenario here is going to be early on under high altitude. And under this situation, you're going to find yourself kind of getting winded, feeling tired and fatigued. And here's the reason why. When we are under kind of high altitude conditions, here's the level of where you fill your bucket up. Okay? So in this case, you're only filling up, and this red doesn't show up as well here, but you are only filling up your bucket to about 93%, let's say, so that when you unload, you really are only unloading to about 30%. So early on, under high altitude conditions, you basically are not filling your bucket completely. So you only fill to about 93%. You still unload kind of to that same point, okay? So that ending point is the same, okay? So you really only deliver, okay, about 30%. So you have about 30% delivery of oxygen. So that's kind of the problem, is you are going back down to this same point. So your unloading is the same. So for both of these situations, your unloading is the same. Okay, so that unloading point is the same, but your loading point is different. Okay, your loading point is here under sort of normal conditions, and then it's going to be here under high altitude. Okay, so you only really deliver about 30% of your bucket versus 38% of your bucket. Okay, so what happens after an extended time? So an extended time at high altitude. And the key here is your body increases its synthesis of 2,3-BPG. So increases 2,3-BPG synthesis. And what that's going to allow us to do is shift to this red line that we have there. So rather than sort of being the black line here, which is sort of normal conditions, we're going to shift to this red line. And now what happens is we bind to and stabilize the T state, and we shift our binding curve to the right. So we bind to and stabilize our T state. Whoops, and this shifts our binding curve right.
I didn't get that. Could you try again?
And it shifts our binding curve right. Okay, so that's what we see with our red line. Now, there's two things that happen here, and I'm going to highlight those with two different colors here. And this is important to indicate that one of these things that happens is beneficial, something that we'd want, and then one of them is not beneficial. It's a cost, but we're going to see that at the end of the day, our costs are going to be outweighed by our benefits. So we're going to have this line, or the difference in these points that we have here, and then the difference in these points that we have here. Because as we go from the black line to the red line, we affect two things. We affect unloading, but we also affect loading. So the desirable thing is we have a beneficial, desirable increase in our unloading. So we have a beneficial unloading effect. So the unloading effect, okay, is going to be desirable. Okay, and that unloading effect means that we are going to take this point and we are going to shift it down to here. This is another example. We already talked about how 2,3-BPG works, right? We're going to be shifting that point down. Okay, so we're going to talk about sort of the importance of shifting that point down. We've seen that before. Okay, and so that is going to be sort of a desirable situation. So that's our green here. So our green here represents an enhanced unloading. We're dumping our bucket of oxygen more, and that's a desirable effect. We do have to kind of point out here that shifting kind of our curve to the right also means we have a loading effect. So the loading effect is actually undesirable, right? So we have an undesirable loading effect. So that's what we're going to show here in our yellow. So what we actually have here is we have an inability to fully load as much as we even would under high altitude conditions under normal, because we've got more 2,3-BPG. So we have a depression in our loading, but we also have a better unloading. And so even though that loading effect is undesirable, the benefit from the unloading is not as much, or is compensated for, is better than sort of this cost that we have on our loading effect. And the point is, here's sort of the money piece, that when we get to a situation here where we have this extended time, oh, I don't want red, I want blue, this extended time at high altitude, what we do is we get back to sort of almost normal oxygen delivery. So let's put this sort of in here, that this is almost normal oxygen delivery. We're at about 37%, where under normal conditions we were at 38%. Okay, now here let's talk about one last piece, like why would athletes then train at high altitude? Okay, so what happens is as we go under, and I'll put a fourth point here. I'm going to put this up top here. I didn't leave myself enough room to sort of talk about this, this piece of it, which is why athletes do this in general. Once we return to normal altitude, now look what happens. Okay, we are going to keep the unloading effect. Okay, and let's see, let's pick a different color here just to sort of highlight all of this. We're going to keep the unloading effect. So that means we are going to keep this point right here. Okay, but now we have normal loading effect. So a normal loading effect. So let's put that in orange as well. So normal loading effect means this point gets to go back to here. So this is why athletes do this. This is why they train at high altitude, is you get to have the benefit of the unloading from the enhanced 2,3 BPG, but by being back at sort of normal concentrations of oxygen in your environment, you get to fill your bucket more fully. So really that adds back in that extra 7%, if you will. So you're going to get now to about 43% unloading. Okay, so you've built up that extra 2,3 BPG reserve so that when you return to normal altitude sort of conditions, you don't have that cost anymore, but you retain the benefit. All right, I know that was a lot to think about, but lots of ways that we can modulate oxygen binding to hemoglobin. And the last thing that we'll talk about in a short separate little video is what happens with sickle cell anemia.